Hi, I'm Kathy Stark. In this lesson, we're going to look at how to identify and graph vertical and horizontal shifts of functions, as well as how these might affect their domains and ranges. We want to begin by looking at some graphs on a graphing calculator. On your calculator, let's start with the graph of x squared. You know by now that this graph is a parabola, but what we want to do is compare this graph to the graph of x squared plus 3, as well as the graph of x squared minus 4. Put these three in your calculator, and let's look at a graph on a standard viewing window. So I'm going to go ahead and zoom 6. There's the graph of x squared, then x squared plus 3, then x squared minus 4. The top graph is x squared plus 3, the middle graph x squared, the lower graph x squared minus 4. This example illustrates how to shift a function vertically. The formal rule is the following. The vertical shifting of the graph of a function works like this. If c is a constant greater than 0, the graph of f of x plus c is obtained by shifting the graph of f of x upward a distance of c units. The graph of f of x minus c is obtained by shifting the graph of f of x downward a distance of c units. The thing to notice is that c is a constant subtracted or added outside the function. Let's try another example, again using the graphing calculator to illustrate. Back to y equals, I want to keep x squared, but I want to clear the other two functions and put in something different. As y2, this time I want to put in parentheses x minus 3, close parentheses and square that. As y3, again parentheses, but x plus 4, close parentheses and square that. I already have a standard window set, so I'm going to go ahead and push graph. There's my graph of x squared. Here's x minus 3 squared and x plus 4 squared. The graph to the right is the graph of x minus 3 squared. The graph to the left is the graph of x plus 4 squared. All of these are horizontal shifts. Here's the formal rule for shifting a function horizontally. If c, a constant, is bigger than 0, the graph of x minus c is obtained by shifting the graph of f of x to the right c units. The graph of f of x plus c is obtained by shifting the graph of f of x to the left c units. It's important to note that the constant is within the function. Subtracted within is a shift to the right. Added within is a shift to the left. Let's try this rule with a different example. In this example, you're given a function and its graph. This is the function f of x is the square root of x. Based on this graph, let's sketch a graph of f of x equals the square root of x minus 2 minus 4. Here's the thing we want to graph. In words, we can see a vertical shift of 4 units down, this amount, 4 down. Inside the function, there's 2 subtracted from x. This is a shift of 2 units to the right. Let me write that down. 2 to the right. We want to graph the same figure that we saw a minute ago, but 4 units down, 1, 2, 3, 4, and 2 units to the right. Otherwise, the shape of the graph has not changed. It's your turn to try a problem. Here's what I want you to do. Sketch a graph of y equals the absolute value of x plus 4 minus 3. Support your answer with a graph using your graphing calculator. Remember what the graph of the absolute value looks like from earlier sections. Stop the tape and try this one, then restart the tape to check your work. Let's see how you did. You should have identified two shifts, a vertical shift of 3 units down and a horizontal shift of 4 units to the left. Let's take a look at the graph of the absolute value, 3 down and 4 left, by graphing this function on a calculator. Going into y equals, I need to get rid of the functions I was using a minute ago and put in the absolute value. One quick way to find it is in the catalog. It's the top item, so I enter on that. Inside the absolute value, I'm going to put x plus 4, then close parentheses for the end of the absolute value. From that, I subtract 3. Again, I'll get a sufficient graph on a standard window, and there it is. Notice that the point, or the v of the absolute value, is 4 units to the left and 3 units down, as we expected. Here's another example given a little differently. Let's see what we can do with it. For the graph given, we want to sketch by hand the graph of each function described in A and B, indicating how the 3 points on the original graph have been translated. The 3 points are -3, -2. This point is 5, 0, and the third is -1, 4. Question A says add 2 to the function. This is a vertical shift up 2. To each of the points, I'm going to add 2 to the y coordinate. That means I want to plot the points -1, 6, -3, 0, as well as 5, 2. Each of these has 2 added to its y coordinate. I'll plot the point -1, 1, 2, wrong direction, 1, 2, 3, 4, 5, 6, right here, -3, 0, and then 1, 2, 3, 4, 5, +2. The graph maintains its original shape just through these new points. Let me label them. This is now the point 5, 2. This is the point -3, 0. And here's the point -1, 6. This is the answer to part A of that example. To do part B, we're asked to take the original and find f of x plus 2. This is a shift of 2 units to the left. To find this graph, what we're going to do is subtract 2 from each of the original x coordinates. Let's find them so we can use them. The original ordered pairs were -3, -2, -1, 4, and 5, 0. We want to take each one of these and shift them 2 to the left. This point becomes -5, -2. This one becomes -3, 4, and this becomes 3, 0. Let's plot this new set of points and draw the graph. I have the point -3, -2, right here. Then -1, +4, and then +3, 0. Again, the graph maintains its original shape just through this new set of points. Let's draw in the graph. Notice it's exactly the same as the original, just shifted 2 units to the left. We want to continue with this idea of vertical and horizontal shifting, but look at how the shifts affect the domains and ranges of functions. Again, let's look at an example. Let's use our graphing calculator to graph y equals the absolute value of x, absolute value x minus 3, an absolute value x plus 2, and then we'll state the domain and range of each. We should expect to see this function shifted first of all 3 units to the right, and then 2 units up. Let's try this out. So in our calculator, for y1, I'm going to use the catalog absolute value and put in x. Don't forget to close the parentheses. As y2, again I need absolute value, but inside it I'll put x minus 3. Again, close parentheses. The third function is the absolute value of x, close there, and then add 2. Let's look at this set of graphs on a standard window. There's the absolute value, then it shifted 3 left, and then 2 up. Based on these 3 graphs, I'd like to write down the domains and ranges, starting with the original. Its domain from left to right is all real numbers. Its range is from 0 to infinity. The one that is shifted to the right has domain all real numbers and range 0 to infinity. The one that's shifted up has domain all real numbers and range from 2 to infinity. Let's write these things down. Keep your calculator screen handy as we write these down. The absolute value of x had domain negative infinity to infinity and range 0 to infinity, including 0. The one that was shifted 3 to the right had domain negative infinity to infinity and range 0 to infinity. The one that was shifted up 2 had the same domain as the others, but its range was from 2 to infinity. Now it's your turn to try one. Here's what I want you to do. Use a graphing calculator to graph the square root of x and the square root of x minus 2 minus 4. With that graph handy, write down the domain and range of each function. Stop the tape and work that problem, then restart the tape to check your work. Let's see how you did. I'm going to start by using a graphing calculator to graph each function. The first function is the square root of x. Make sure you close parentheses after the x. The second function is the square root of x minus 2, close the parentheses there, and then subtract 4. Let's look at a graph, and from the graph, state the domains and ranges. This first graph is the graph of the square root of x. From left to right, its domain is from 0 to infinity. Its range, from bottom to top, is also 0 to infinity. The second graph is shifted 2 to the right and 4 down. From left to right, its domain is from 2 to infinity. Its range is from negative 4 to infinity. Let's write these things down. The square root of x has domain 0 to infinity and range 0 to infinity. This graph, because it is shifted 2 to the right, has domain from 2 to infinity. Because it is shifted 4 down, has range from negative 4 to infinity. In this lesson, we've looked at how to vertically shift a function and horizontally shift a function. Keep in mind that a vertical shift is identified by a constant outside the function and a horizontal by a constant inside the function. We've also seen how the domains and ranges of functions are affected by shifting them. Be sure to practice lots of problems from your textbook to reinforce this material.